As we've seen, if we include damping in the equation, as we've defined here, our equation for the oscillatory system becomes this. We've solved the homogeneous equation. We see that there are three cases depending on how big the damping constant is. And we're going to be mostly interested for now in the case where we get the two complex solutions. But that's not going to be necessary to solve the non-homogeneous equation, and that's where we're going to go here right now. So the non-homogeneous equation, just having written the equation down again, is this. And we're going to assume a particular solution of the form A cosine omega naught t plus B sine omega naught t. Now you recall that not too long ago we had to assume AT cosine omega naught t plus BT sine omega naught t. Why don't we have to do that this time? Well, before we didn't have this damping term in here, so that the cosine of omega naught t and the sine of omega naught t were solutions to the homogeneous equation. In this case, the solutions to the homogeneous equation, in the case where we have the oscillatory behavior, has angular frequency omega square root of omega naught squared minus delta squared, as we saw previously. So that the driving frequency is no longer equal to the natural frequency of the system. And since it's not, I kind of wonder why I went ahead and why I called this omega naught when I could have gone ahead and called it omega 1, but it really doesn't hurt anything, so let's just keep it the way it is. Having assumed this solution to the non-homogeneous equation, we take the two derivatives and we plug those the three functions, the two derivatives and the original function, back into the original equation, which gives us this. And I'm not going to belabor this because the process is identical to that we followed previously. The details are a little bit different, but we plug these solutions in, we do the arithmetic or the algebra, and we simplify to the form where we have something multiplied by the cosine of omega naught t, something else multiplied by the sine of omega naught t, and of course that's going to be equal to our right hand side, which is a multiple of the cosine of omega naught t. This leads us to the conclusion that whatever is here has to equal f over m, and whatever's here has to equal 0. Now, I haven't simplified this term, but we notice that we have a negative omega naught squared a and a positive omega naught squared a here. So that actually there was good reason why I chose the natural angular frequency that would occur in the absence of drag. If I hadn't done that, these two terms would not have added up to 0, nor would these. But since they do, we're just left with 2 delta omega naught b times the cosine of omega naught t, so that the 2 delta omega naught b has to equal f over m. So we get this equation, and that this term, being the only term left in this coefficient, has to equal 0 since it's the coefficient of the sine function, and there's no sine function on the right hand side. So we get these two equations that are very easily solved for A and B. A is going to have to be 0, and B is going to be f over 2 delta omega naught m. Now the solution for delta less than omega naught, and let's make sure we understand that that's what we're talking about here, is the one for which we end up with the angular frequency square root of omega naught squared minus delta squared, and the exponential attenuation e to the negative delta t that results from this solution that we saw previously, so that our function becomes this. And this part of our solution is exponentially attenuated, that means it exponentially disappears on some long or short time scale depending on the value of delta. And it has angular frequency square root of omega naught squared minus delta squared, which is less than omega naught. This non-homogeneous term has angular frequency omega naught, and it has a constant amplitude. So we have constant amplitude, so that this term eventually takes over our solution no matter what our initial conditions are. After a while, this part of the oscillation goes away and this part of the oscillation takes over, so that this dominates after a while being a distinctly non-mathematical term unless we choose to define it. But I'll leave that to you. The other thing that we note is that this exponentially attenuated form, and we can call this transient. Didn't quite get the whole word in there, but the word is transient. Is at a different frequency than this, so these two are going to become in and out of phase, which is going to have a significant effect on the behavior of the system, while the amplitudes of these two contributions are comparable. So I can say, if I've got room to write it down here, the transient and long-term behaviors I'm going to write that as come in and out of phase I'll say resulting in beat-like behavior, and you can look up what that means. When the amplitudes are comparable. Now, you can probably get through this course without completely understanding that, although you never know what's going to occur on a test. But if you really want to understand the behavior of systems and how differential equations illuminates the behaviors that we see in the real world, you might want to think about that. Again, reading this to you, because you might not be able to read it, it's kind of small. Here's the transient. It's exponentially attenuated. It's got an angular frequency that's less than that of omega naught, obviously. And we have the long-term solution. I didn't write long-term down here, but it has an angular frequency omega naught with a constant amplitude, and it dominates after a while. And then the transient long-term behavior come in and out of phase, and that results in beat-like behavior when the amplitudes are comparable. There's a time, as these things are reducing in amplitude, that the amplitude of this contribution is comparable to the amplitude of this contribution. And you can, again, and I recommend that you do, look up what beats are in physics.